Hi everyone! In the previous video, we studied the execution of I/O. We realized that the default mode of operation for I/O is sequential. This is what happens when we combine I/Os using a for comprehension or other methods of the I/O API, such as zip, sequence, or traverse. So this pushed us to develop new methods to combine I/Os concurrently, namely parzip, parsequence, and partraverse. To a mixed success. We did manage to execute a few I/Os concurrently, but our implementation was extremely inefficient and could lead to deadlocks because all concurrent methods were built on top of parzip, and parzip was blocking. So the goal for today's video is to make our I/O implementation suitable for concurrent programming. This will help us to get a better understanding of libraries such as Ch05, Monix, and Zio, but also how their design differ from features from the standard library. Once again, I would like to warn you that this video is quite advanced and should really be seen as bonus material. Okay, so the important question is, why is parzip blocking? It's blocking because we call the method await.result on a future. And why do we call await.result? Because we need to return a tuple A other in order to produce an I/O of tuple A other. Indeed, if we look at the apply method of I/O, we can see that to create an I/O of A, we need to pass a value of the same type, or at least a function that returns an A. That's essentially what a byname parameter is. And why does the apply method have this specific signature? This is because to create an I/O, we need to implement unsafe-run, the only abstract method of the I/O trait. So ultimately, parzip is blocking because the I/O interface is implemented in terms of unsafe-run, and unsafe-run is also blocking. It becomes clearer if we compare the signature of await.result with unsafe-run. Unsafe-run takes an I/O of A and returns an A, while await.result takes a future of A and returns an A. So unsafe-run is the equivalent to await.result with an infinite timeout, meaning that we wait for the result until it is available. Okay, so to implement non-blocking concurrent combinators, we need to base the I/O definition on method other than unsafe-run. What should it be? Let's have a look at future once again to get some inspiration. We say that future is non-blocking, but what does it mean exactly? It means that when we create a future, we don't wait for the code inside the future to complete. For example, when we call db.getUser, we get back a future immediately. We don't wait to receive a user record from the database. The rest of the future API behaves similarly. For example, when we call map, it doesn't wait for the result of the current future. Instead, it immediately creates a new future that says, when the previous future is complete, do this extra operation. In other words, the future API reacts when the result is ready. This is also called asynchronous programming. A good example of this pattern is the method onComplete. OnComplete takes a callback function, which is called when the future is done. You can think of it as a notification which contains the result of the computation. It can either be a success or a failure. For example, if we call db.getUser.onComplete, it will fetch a user record from the database, and when the DB responds, it will print a message to the command line. What's important here is that this entire operation is non-blocking. It all happens in the background. This means that we can easily fetch another user concurrently. We only need to repeat the same logic with another user ID. And contrary to what happens with parzip, the main thread isn't blocked at any time. Cool, so with those insights, let's try to modify I/O so that it's based on the method onComplete instead of unsafe-run. I/O libraries often use a different name for onComplete. They generally call it unsafe-run async, where async stands for asynchronous. So we're going to keep this terminology. Now let's go to the file io.scala, and the first thing we're going to do is to define an abstract method unsafe run async, which is going to take a callback function that takes a try of A and returns unit. And this whole function returns unit. So unsafe run async is going to be the only abstract method of the I/O interface. So we can actually move this comment over there. And so this means that we should either remove unsafe run from the I/O API. For example, we could define it in a separate object, similar to what Future does with await.result. Or we could keep unsafe run here, but implement it in terms of unsafe run async. We'll do this a little bit later. For now, let's use a triple question mark for unsafe run as a placeholder. Now, if we compile this project, we expect to see a bunch of errors because we changed the encoding of the I/O trait. Surprisingly, we only got one in the apply method of I/O. This is because apply is the only method we use using the new keyword. As a side note, when we develop an API based on traits, it's good practice to limit the usages of new as much as possible. This way, when we make changes to the API, there is very little code that breaks. Now it's your turn. Please pause the video and try to re-implement apply based on unsafe run async. Note that we don't have an execution context available in the apply method. So this means that we're going to execute the by-name parameters locally. Later on, we'll add methods to dispatch the execution to the thread pool. So please pause the video and give it a try. Okay, so to implement this apply method, what we're going to do is that we need to call callback somehow. Callback is like a custom return function. So it's, in Java or some other languages, you end a function with return and you do something. Callback is like a custom return function that we are passed. This is what we're going to do afterward. So we need to call callback at the end, which needs to be a try of A, right? So how do we get a try of A? We need to execute the by-name parameter here. So we'll say, okay, result is of type try of A, and which means that we need to evaluate action, and we need to wrap it in a try because we know that it can potentially fail. So once we have it, we pass it to callback, and that's it. Now, at the moment, as I mentioned it, is that now apply execute the action in the current thread. We don't dispatch it to an execution context. But nothing blocks us for defining another constructor of I/O, let's call it, for example, dispatch, that will say, okay, let's get an execution context. And what we'll do is that within the unsafe run async, we're going to dispatch the execution somewhere else. So we could use a future to do this, but we can also use directly the execution context API. So if you look at execution context, it has a method execute that takes a runnable. So we can say new runnable, which is going to be executed on the thread pool. And basically, within this runnable, we are going to copy paste whatever code we had here. So I just need to add curly braces, and that's it. So if you want, this is doing exactly the same as over there, except that here it's done everything locally, and here it's done on the thread pool. Now we can simplify the code slightly. We don't need to have two steps. We can just do it like this. Same here, just to make it slightly more concise. And the same, runnable, because it's a trait with a single abstract method, potentially we can also use the SAM syntax, which means that we can replace this by that. So the SAM syntax basically says, because this trait has a single abstract method, let's just define this method straight away, and that's it. So really, the only difference between apply and dispatch is where we execute the callback function. And this is something we couldn't do with the previous implementation. Here we can see an important difference in design between I/Os and futures. Futures always dispatch the execution to a thread pool, while I/Os may or may not do this. It's completely up to us. This is a very important point with regard to achieving maximum performance. because dispatching the execution to a thread pool has a cost. It introduces some overhead. So we only want to do this when the task is big enough. Let's take an example from the real world. Say we want to eat a pizza. We can either order it ourselves by going to the restaurant, waiting for the pizza to be made, and going back home, or we can delegate the task to a delivery person. In this case, the delivery will probably save us lots of time. However, if we just want to get a glass of water from the kitchen, it doesn't make sense to ask someone else to fetch it. It's going to be much faster for us to do it ourselves. So the same goes with I/O. If we want to fetch data from a third-party service, it probably makes sense to do it in a separate thread. But if we want to calculate the size of a list, it's probably better to do it in the current thread. Now, before we move on, I would like to define a new constructor for I/O based on unsafe run async. It will help us in case we want to change the I/O encoding later on, and it also provides a more consistent syntax. So let's call this method async. That's the names chosen in Cat's effect. So async is going to take an A and returns an I/O of A eventually. So it will take some parameters, but we don't know yet what's going to be. And this is going to call the new I/O constructor. And here we'll implement unsafe run async. So the goal is that async should be the only method that uses the new I/O constructor, and everything else will be based on async. So now it's going to be, you will probably find the signature very weird, but the idea is to take the signature of unsafe run async and basically copy-paste it and pass it as input here. So this means that this is going to take the callback function and it will return unit at the end. So this, instead of being called callback, it's probably more onComplete or, yeah, onComplete. And so now the goal is that the implementation will be very straightforward. It's just onComplete with the callback. Now, take some time to review this signature on your own. Really, this onComplete method is just the same signature as unsafe run async. It's something that takes a callback function. This is a callback function. And eventually, at the end, it returns unit. And we just do that in order to have only one place where we use the new I/O constructor. So this allows us to refactor apply this way, and same for dispatch. So now it's a bit more clear, they're a bit more readable, and also if later on we change the I/O API, supposedly only async will break. So it's not required, but it's a good practice. Now if we run the test for I/O, everything will fail. This is because unsafe run is not yet implemented. You remember at the top, at the moment we use triple question mark as a placeholder, so that's why kind of almost everything is broken. So now what we need to do is to implement unsafe run in terms of unsafe run async. So I'll let you pause the video and give it a try. Okay, so how are we going to implement unsafe run? So we know we need to call unsafe run async because this is the only method we have access. So we'll say unsafe run async, and now we can do an exhaustive pattern match to say, okay, either it's going to terminate with a failure, which is an exception, or with a value of type A. So we could say, okay, if it's an exception, let's throw it, and if it's a value, let's return it. However, if we ask it to compile, you see it doesn't work because unsafe run async returns unit, meaning that this code, this callback function, may be executed in a separate thread, it may execute it later, we don't really know. But we need to return an A. So somehow it means that we need to pass whatever we get from the callback function and to pass it back to unsafe run. So one way to do this is to basically create a variable and say, okay, this will be the result of our function. And so let's call it an option of A. So it will be initialized at none. And then within the callback, what we'll do is that we're going to set this variable. We'll say, okay, result will be equal to sum of value. Okay, let me do this. So this means that whenever the callback will be called, so it may be right now, it may be later on, we are going to update the variable, and then at the end, we can do result.get, meaning that we expect this option to be not none once we call this. Now actually we also need to do the same for the exception, because this also may be thrown somewhere else, while we want to throw it within unsafe run. So what we'll need to do is that instead of doing an option of A, we need to make an option of try of A. And so here we'll say some success, sorry. And here we're going to do sum of failure with the exception. So if you want, at the moment what we do is that whatever we get, we just save it inside of the result. And then at the end, we're going to call twice get, once to unwrap the option and once to on the try, meaning that if the try is a failure, it will blow up, which is what we want, and if the try is a success, it will give us a value inside it. So this means that we can slightly clean up this code, because you see, if it is a failure, we set a failure. If it is a success, we set a success, which means like, this is a try of A. And what we want to do is that whatever we get from the callback, we want to save it in the variable, right? So it's the same thing, it's just slightly more concise. Cool. Okay, so let's run our test to see if it works. Yes, all good. That's quite nice. Now, it only works because everything within the IO test are based on io.apply, and io.apply don't dispatch the execution to the execution context. For example, let's write a test that will most likely break. So imagine we write a test for dispatch. Dispatch should behave basically like, like apply. Dispatch. So imagine if you say io.dispatch, counter +1. You expect, and also I also need an execution context, so I can say execution context.global. Now, io.dispatch, the only thing that it does is that it does the +1 in the thread pool instead of doing in the current thread. But it should give us the same result, right? It should be the same as io.apply. But if we run the test, I bet that it's going to fail. Yes, it does. At the moment, we see none.get, meaning that at the moment, when we call result.get, the value of result is equal to none. This is because the callback function, the one we call, this method here, is only going to be executed in another thread, which means that there is kind of a race condition between this result here and this callback here. So sometimes, it's possible if we run this test many times, it's possible that sometime it will pass if the execution is done immediately, but most of the time it will fail because result, this value here, will only be set to sum later on. So what we really need to do here is somehow at that point, we somehow need to wait for the callback to be executed. So I'll let you pause the video if you haven't done it and try to somehow wait for the result to be complete. So please pause the video and give it a try. Okay, so what we want to do here is basically wait until a result is non-empty. So what we could do is to have a while loop that verifies that as long as the result is empty, we want to wait. So we want to do like a thread.sleep. So we could do while result is empty. So while this callback function hasn't been called yet, we can do a thread.sleep with a very short amount. So let's say 10 milliseconds. So this will check if the result is empty. If it is, it sleeps 10 milliseconds. Then it checks again if the result is empty. If it is, it sleeps 10 milliseconds again, and so on. And once the result is non-empty, we'll go further and we'll return the result. So let's give it a try. Yes, it all works. Now, instead of doing like many small sleep, there is a slightly more efficient implementation based on concurrent data structures. To be honest, I would not have known about it if I didn't check the source code of Cat's effect. But this is called a countdown latch. So it's part of the Java library. So you can a countdown latch. And let's have a look at the documentation. So it says that it's a synchronization aid that allows one or more threads to wait until a set of operations being performed in another thread completes. So this is exactly what we want. We want to complete the callback function in another thread, and we want to use this countdown latch to basically wait for this callback operation to complete. And how does it work? You initialize a countdown latch with a number, and this is how many times the countdown function should be called. So if you want to wait for 2 operations to be done, you will set a countdown latch to 2. But here we only want 1 operation to be done, this callback function to be called. So then at the end, what we're going to do is we'll say latch.await. So latch.await is going to wait for countdown to be equal to 0. As long as countdown is not equal to 0, we'll block forever. So this is really the same as doing this while the option is none, we keep sleeping. So this is the same, it's slightly more efficient. Now we do need to eventually release the latch. So this means that after we set the result, we need to release the latch. And how do you release the latch? You call latch.countdown. And this will basically release the latch. So this blocks and this releases. Let's rerun the test. Yeah, it all works. So I just wanted to show you these are 2 options. This one is slightly more efficient, but to be honest, the thread.sleep also works perfectly well. Cool, so now that we have all the building blocks, we can go to parzip implementation and try to make it non-blocking. So this is going to be quite tricky. We'll try to do it in several steps. So the first part, we need to remove this await.result. So I will let you give it a try. I'll just give you a hint. So instead of calling io.apply, we need to call io.async. And somehow we need to call this callback function without blocking the future. So I'll let you play around and give it a try. Okay, so let's try to do io.async. So this is going to give us a callback function. By the way, one thing quite nice is that the type inference in Scala, you see it's quite powerful because here we don't say what is the type of async, and somehow it figures out that it's a tuple a other. So we know that callback takes a try a other and returns unit. So somehow we need to call this callback function here without blocking. So we want to remove await.result, and somehow here we want to call this callback when zip is ready. So which method in the future API let us call something when the future is ready? We have map, but we also have onComplete. So onComplete is exactly the method we need. If you look at onComplete, it takes a function from try a other to u is whatever we want. So this is perfect for our case. And at the end, we also need to pass an execution context. So if you want, what we've done here is that we said, instead of waiting for the future to be complete, we say, here is what we need to do after. So this is what we need to do once the result is complete. And we just let the future API to basically append this callback function at the end of the computation. So we don't block anymore. We just tell the future API, here is what you need to do after. Okay, so let's try to go to concurrent example and try to see, let's go back to 4 threads. And try to see if it fixed the problem. So hopefully it worked. And no, it didn't. You see now we see only F and D, and they all execute in one thread. So it seems that what we have done is not enough. So let's go back to parzip and let's try to figure it out. So now we don't block anymore in the last operation here. But if you think about it, we do block here and here, and safe run is a blocking operation. So even though we don't block the parzip function, every time, like when we dispatch the 2 threads, we do block there. So we also need to remove this blocking over there. So could you please pause the video and try to remove unsafe run from these 2 lines? Now this is very tricky. You kind of need to know a bit the future API in order to do it. But let's give it a try. So basically what we need to do is to change future 1 and future 2, that instead of using unsafe run, it should use unsafe run async, because we don't want to block anymore. So this, if you want, is going to return a try of A, and this result So this try of A is a result of the current I/O computation. It may be a success or a failure. And somehow we need to do something with this result. Now, one thing important is that you realize once we do this, once we use unsafe run async within the future constructor, this doesn't give us a future of A anymore, it gives us a future of unit, which sucks because once if future 1 is a future of unit, we can't zip with future 2 anymore because with future of unit, we can't zip them and then call the callback function. So it's not going to work. So actually, we do need to call unsafe run async, but we need to have a look a bit at how the future API works behind the scene. And a very important aspect is something called a promise. So a promise, let me show you how it works. So a promise has a type parameter, it tells you what you expect, and initialized like this. So if you want a promise, is roughly the same as a mutating variable, so it's like almost as if we had said promise 1 is A, and it's initialized to like nothing. Except that a promise can be set only once. So if you want, once you set a variable to the promise, it's initialized empty, and once you set the value inside it, you can't change it anymore. It's done once and for all. And that's basically why the future API cannot be retried, because once you set the promise, you can't change the value inside it. And the nice thing is that once you have a promise, you can transform it into a future by using promise.future. So this means that if we create two promises, one for an A and one for other, so this will be a promise to is basically an other, then we can say, let's combine the two promises together and zip them, and then let's leverage the onComplete function like before. So if you want, it's a bit magical, but we really rely on the promise API and future API to do the right thing. The only thing that we really need to do is somehow set this promise at some point. Okay, so what does it mean? It means that we need to send the execution to a thread pool, and within this runnable, we need to set the promise. So let's try to do this. We do ec.execute. So this takes a runnable, but we can inline it like this. And within this, we need to set promise 1, and we'll do the same for promise 2. So this means that we need to run the current I/O. So we'll do unsafe run async, because again, we don't want to block. We want to do everything asynchronously. And this will give us a try of A. So try of A is a result of the asynchronous result of the current action. And somehow, we need to populate the promise with this try. And so let's have a look at the API. There is a method called complete. And complete takes a try of A, so exactly as we want, and complete the promise with this try. So if you want, if the try is a success, it will complete the promise successfully. If it is a failure, it will complete it with an exception. So this means that we need to do complete try of A. That's it. And in fact, because here we get a try and we pass it immediately, we can slightly make it more concise, like this. So really what we say here, let's submit a computation to the thread pool, and within this computation what we do, we execute the current action, and once it's done, we set the value to the promise. And we can do exactly the same thing for the other I/O, and this time we'll set promise number 2. Cool? So let's see if it compiles. Yes, it does. Okay. So let's give it a final try for concurrent examples. Now this time, nothing is blocking. It should work. And it doesn't. So we are still not there yet. We must have screwed up somewhere. So we still see F, E, and D at the end. They are all in the same thread. So what could be wrong, really? Now, inside of parzip, nothing is blocking. We don't have any unsafe run anymore. We don't have an await.result anymore. But what's wrong here is that we still have some methods within the I/O APIs that are based on the unsafe run. Because when we change the I/O API from unsafe run to unsafe run async, we haven't updated all the functions within this I/O function. So let's review methods one by one. So unsafe run, it's fine, and then it's based on flat map. This is based on and then, this is based on flat map. Ah, here we are. So flat map, at the moment, run the current action, so block to run the current IO, then call the second IO and block again. So at the moment, flat map is completely blocking. So this is probably what the issue that we have. So could you please pause the video and try to refactor flat map so that instead of using io.apply, it uses io.async. Cool, so please pause the video and give it a try. Okay, so let's try this plan. So we'll use io.async instead of io.apply. So this will give us a callback function. And whenever we use unsafe run, now we need to use unsafe run async. So maybe let's erase it completely. First thing we want to do is run the current IO. So we'll use unsafe run async, and this will give us back a value. So we can use an exhaustive pattern match. Okay, so what do we do if the current IO fails? If the current IO fails, we can't call this callback. Oh, by the way, you see that we have callback. This is a problem. So let's rename this function here to next. This is a function that will give us what to do next, while callback is the final thing that we'll call at the end. Okay, so let's review it. Imagine the first IO, the current IO fails. What can we do? We can't really call next, because in order to call next, we need to have an A, but we only have an A in the success branch. So here, we need to fail early. You know, this is a concept of a for comprehension of flat map. It fails early. As soon as an IO fails, it stops. It doesn't go further. So this means that we need to call the callback with a failure. So we basically say callback with the failure. So this will be the equivalent to failing early. Okay? Next, so here value is of type A. So we are in lock. This means that we can call next with value. This will give us an IO of next, which we again need to call unsafe run async. So let's repeat the same process. Let's do an exhaustive pattern match. If it is a failure, for the same reason as before, we're going to call the callback with it. And if it is a success, so here this is a next, so we want to call the callback, and callback takes a try of next. So we need to say success of value. Cool. So actually, you see, if it is a failure, we call callback with a failure. If it is a success, we call callback with a success. This means we could simplify this to say, okay, this is a try of next. And basically, whatever is the value of try of next, we are going to call it like this. So this will make the code slightly simpler. And in fact, we can even do better, because here we create a variable and we pass it straight away. So again, we can remove it like this and just say callback, which makes it, you know, slightly more readable. We say, okay, let's run the current IO. When the current IO fails, we call the callback with a failure. So this is the early termination. If the current IO succeeds, we call the next function, which gives us an IO. And what we say is that basically, whatever it's done, call the callback. So we just propagate the thing. OK, so let's hope that this time it will work. So let's rerun concurrent example. Awesome, it works, finally. So now we can see that all the IOs are executed in different threads. We are not blocking anywhere. So we see the F, the D, the E, the C, everything else. And at the end, it's terminated. So it's not deadlocking anymore. What we can do as well is to try to reduce the thread pool. So for example, if we say if we only have 2 threads, let's see that if it works. Let's see if it still execute concurrently. Yeah, it still works. Now we only have 2 threads. We have 0 and 1, and they still are like interleaved. And if we put only 1 thread, it should still work. It should execute like sequentially, because we only have 1 thread, but it shouldn't block. At least it should progress. Yes, exactly as expected. So now we see we only have 1 thread, pool 0, and all the IOs execute one after another. So everything works fine. Now, as a bonus exercise, I will ask you to review the IO API. I believe there is still one method that uses unsafe run. I think it's attempt that it still uses unsafran instead of unsafran async. So potentially this means that we are still blocking for all the methods, for all the error handling methods. So as a bonus exercise, I will let you re-implement attempt using unsafran async. In summary, today we transform our I/O encoding so that instead of waiting for a result, we react when the result is available. This was a very subtle change, but it allowed us to remove all blocking code within I/O, and as a result, we could implement parsif and parsequence relatively efficiently. One way to visualize the evolution of our I/O implementation is to imagine that we want to order food from two different restaurants. For example, maybe we want to have the starter and main course in one place and the dessert somewhere else. So we could fetch the food ourselves, which means we go to the first restaurant, order the food, wait for it to be ready, and repeat the same process at the second restaurant. This is essentially how the first I/O implementation worked. Everything was sequential and done in the main thread. Then we work on concurrent methods for I/O, which would correspond to ordering the food online at each restaurant and asking for a delivery. So this is much more efficient. Both orders are made concurrently. However, our implementation was blocking, which is equivalent to waiting at the door after we place the order. This is a huge waste of time. We could spend an hour waiting for the food to arrive. So finally, we solved this problem using unsafran async. Now, instead of waiting at the door after we place the order, we do other activities. At some point, the delivery people will let us know that the food is ready, and we can come back and collect it at the door. So if there is one thing to remember about what we have done today, is to avoid blocking as much as possible. This means that we should avoid using unsafran in our production code. The only exception to this rule is in the main of our application. It's fine to call unsafran there because we need to execute the I/O at some point. Otherwise, nothing will happen since I/O is lazy. Cool, so I hope you enjoyed this video, even though it was probably very difficult. Concurrency and callback-based API are tricky to get our head around, and the terminology is super confusing. If you want to learn more about this topic, I will encourage you to watch Fabio Labella's presentation called How Do Fiber Work? It is a brilliant presentation on the topic. I will put a link below the video. See you soon.